Tribology is a field of study that relates to lubrication, friction, and wear. And definitely, tribology is at the heart of machine reliability. A well-known tribologist is a professor by the name of Ernest Rabinowitz from MIT, Massachusetts Institute of Technology, recently deceased. He's well known for making this statement. He said 6 to 7% of the gross national product, a few years ago, this was about $795 billion, a big number indeed, is required just to repair the damage caused by mechanical wear. That's a big number, but it's not the biggest part of it. The biggest part is the business interruption associated with downtime, with failure. The cost of lost production and downtime is often estimated to be somewhere between 5 and 10 times the cost of the repair. Then you have fuel consumption costs and other associated costs related to failure and wear, including safety risks. So it's an important number. We know that 2 plants running at 50% utilization, meaning they have downtime associated with the other 50%. 2 plants running at 50% utilization is doing the work of 1 plant at 100% utilization. Professor Rabinowitz also gave us this chart here relating to the loss of usefulness of equipment. He says there's 3 ways machines lose their usefulness. One's accidents, the other is obsolescence, and then the main way is, which he refers to as being 70%, is surface degradation. What's unique about the surface degradation is that it's a controllable area of wear and loss of usefulness. Again, relating to roughly 70%. This is very similar to losing kind of tread on our tires. It's something that happens little by little over time. And eventually you lose too much tread and you have to change the tire. Same's true with a machine. You have frictional surfaces that wear little by little over time, and eventually you have to fix or replace or rebuild. So the machine kind of eats itself up little by little from the inside out, we could say. And this surface degradation is what we need through lubrication, through tribology, through oil analysis, through maintenance activities to try to control. There's 2 types of surface degradation loss, according to Rabinowitz. One is corrosion, which corresponds to about 20%, also known as chemical wear. This includes rust and erosion and similar chemical-induced, surface loss mechanisms. Then we have mechanical wear being the larger of the 2, 50%. So this is physical damage from rolling and sliding contacts. Underneath mechanical wear are 3 subtypes of mechanical wear. The first is what we call adhesive wear. This relates to sliding contact conditions where the surfaces are not separated by a nice cushiony oil film, but instead are touching. They're rubbing, they're galling, they're scuffing, they're adhering. A lot of heat's being generated between those surfaces, and as a result of that, we have deformation and wear, material transfer, and material loss to the lubricant there. So that's adhesive wear. Fatigue wear is a rolling condition. It's kind of like trucks going down the highway. Over time, the pavement kind of gives way due to too many stress reversals associated with the loading on the truck. It's kind of like bending wire. You bend it enough times and it breaks. The same's true with the loaded surfaces within our machine. The raceway or track where a rolling element, moves, or it could be a ball in a raceway, and the rolling element itself. Eventually, these surfaces fail, and they fail due to load, they fail due to contamination, and loss of film thickness. And so that's what we call a fatigue wear. It's a rolling contact condition. Then we have abrasion. Abrasion is sliding contact, just like adhesion, but here we have actually 2 types of abrasion. The first type is what we call a two-body abrasion. This is the hard surface filing and cutting the opposing softer surface. So these surfaces microscopically are not perfectly smooth. They're, if you look at them, under a microscope, you'll see that there's peaks and valleys. The peaks are what we call asperities. They have the ability to cut and carve and scrape and scratch, damage the opposing surface, especially when there's not a nice oil film separation there. So again, that's two-body abrasion. It's a filing action. Three-body abrasion, there's a third component here, and perhaps you've already figured out that that third component is a solid particle that gets interposed between these surfaces, sliding surfaces, in relative motion. So the particle has to be, of a specific size. If it's too large, it can't make it in the gap. If it's too small, it just kind of shoots the gap. It goes through, it doesn't bridge that working clearance, can't do any damage. But if it's the right size, then the surface kind of clamps down on the particle. The particle will sink into or embed into the softer of those two surfaces. And now that particle has the ability to damage the harder of those two surfaces. Could be a shaft, and then the softer of the two surfaces being bearing metal, for instance, like babbitt. It could be brass, bronze, aluminum, or other soft metals there. So it's a little bit like dropping a bar of soap into sand. You pick it up and you have all the little sand particles in the soap. Very similar to that. In fact, many of the particles that we're most concerned about are actually environmental particles, silica and alumina. And these particles that are floating around are on the streets and roads and floors and so forth, they do find their way in our machines and in our lubricants. And the lubricants, of course, is a transport that brings these little particles in between these sliding surfaces and enables them to cause this three-body abrasion. If I went outside and got a typical handful of dirt, generally about 2/3 to 3/4 of the particles in my hand would be hard enough to scratch a hacksaw blade, high-speed steel. So we have particles all around us that have the potential to do a lot of damage, and they do a lot of damage, and that's what we call abrasive wear. So the strategy here is to understand what causes surface degradation. So we've talked about corrosion, we've talked about mechanical wear and adhesion, fatigue, and abrasion. And by understanding these wear mechanisms and these surface degradation mechanisms, we can work our way backward to the things that we have the ability to control, the things that achieve, working clearance and films within our equipment and reduce wear, the selection of lubricants, the selection of filters, and so forth. And from that, we can achieve we can slow down the rate of wear within our equipment and substantially extend the life of our equipment.